Hello, I'm Giles. I'm going to tell you guys stuff about automated refactoring, the art of building robots to fix code for you, because fixing bad code is tedious and repetitive work is what computers are for. So that's what they should do. But you have to walk before you can run. So refactoring. This is the sort of canonical text on refactoring. It is called Refactoring. And the subhead is improving the design of existing code, which is actually a really important distinction. A lot of times when people say I'm going to refactor this, they actually mean I'm going to rebuild it, redesign it, fix it in some way. But if you're adding new functionality, you're not refactoring. So why do you do it? Are you just rearranging deck chairs on the Titanic? Basically, the idea is that good design is easier to work with. Like once you've hammered out your implementation, you want the good design to emerge from it. And if you are going to be adding more functionality or changing the functionality, you will have less headaches the better your design is. There's a lot more to it than that, but this clock represents the limits of time, and I have some limits of time. So before I talk about automated refactoring, here's an interesting surprise. Spreadsheets are incredibly useful for refactoring, right? Say you have some incomprehensible code, right? And you're looking at it like, OMG, WTF. Yes, it's a cat with a Rubik's Cube. Yeah. I have to assume the cat does not have color blindness, but you never know. So as we all know, OMG WTF, it stands for oh my god, what's this function? All right? So you're here, and this is more or less where you want to get to, right? This is called there I fixed it. It's a happy place. But the good news is you have specs, right? Or tests. And again, the bad news is that if you don't have them, you'll need to have them before you can proceed with refactoring. But say you have these specs and these tests, and you have this code, which is incomprehensible, and you're trying to get from OMG WTF to there I fixed it. If you have specs and tests, you can go on a killing spree, right? Like this guy. But a killing spree of code, just to clarify, with a spreadsheet. And what I mean by that is you take, this is an actual spreadsheet that I made when I was refactoring some code. And I literally just, the first column is lines changed. And the change was simply deleting the line, right? And I went through this incomprehensible method, deleting individual lines, running the specs, and counting the number of failures that were triggered by deleting any particular line, and then, you know, just undo the change, restore it, and then go down to the next line and delete that. And what I tracked was the spec failures in the first column and the failures only in the transaction spec, it was code around transactions, in the second column. And that was just to differentiate between intuitive failures that were easy to explain and counterintuitive ones which were, you know, mysterious or confusing. And it kind of gives you a good metric for like code significance, right? Like down at the bottom, there's two that if you change either of these lines, you get over 30 spec failures. But the interesting thing is that one of these, it'll cause 32 spec failures in general and 7 in the relevant spec file. And the other one caused 37 failures in general and 18 in the relevant spec file. So the latter, the failures were more, you know, almost constrained to the relevant file, which is what you want to see. Like in the ideal world, when you delete a line in an implementation and then you run the spec against that implementation, you should only see numbers in the second column, right? All the other specs should work just fine because there's, well, it depends on your definition of ideal. But the point is, this little spreadsheet actually gives you like an interesting metric for code fragility or how important any given line in the method is. So even though this code was incomprehensible, it was prioritized. I knew which incomprehensible piece to figure out first. And that is one way to get from here to there. Now, a similar use for spreadsheets, another time I had a bunch of methods and I wasn't sure that they did anything. Okay? This is CoffeeScript, right? It's not actual code from the project, right? Although it's not much different. But what I wanted to know was, do these methods which appear to do nothing actually do nothing? It's one of these problems you got to face if you're dealing with bad code. So I used ACK and WC, two Unix utilities, to find out the number of times each method appeared in the code base. Right? ACK is like grep. Do people know what grep is? Raise your hand. Grep? Okay, cool. So ACK is like grep, but better. The website is better than grep.com. Truth in advertising, in my opinion. And WC stands for word count. WC-L means line count, so it counts the number of lines. So if you run that search, you'll get the number of times it appears in the code base. And then I made a simple spreadsheet in my text editor. It is not, I have changed the names of the methods to protect the guilty. All right? This is stamp rainbow event, stamp unicorn event, stamp bunny event, and so on. It was not actually an application that concerned unicorns, rainbows, and bunnies, but it could have been. And anyway, what I found is that I was right, and two of the methods were literally useless. They were not used in the code base anywhere, ever. And I can tell you, as someone who has had to refactor code from time to time, when you refactor code, you will find this sooner or later. Somebody wrote something they thought was going to be really useful, and they just forgot about it. And this is one way to find that. So obviously, it's very clear what to do in that case. Now, this is going to lead us to some actual automated refactoring. All right? Sometimes you get really similar code. Can you guys see this, like at the level of individual letters and words and shit? Yeah? That's a thumb or it's a W? What? Okay. I don't know what that is, but that's good. Okay, so you get incredibly similar code, right? And it's a pain in the ass to figure out what the differences are. But if you look, they're there, right? Bar should be, here it says bar and baz, here it says baz and bar, right? This is another time where I throw out the text editor and I actually switch to an actual spreadsheet app, and I do something like this, where you put the file name in a column, the argument for foo, the argument to the anonymous function, and you literally track these things so that you can say, you can step back from it and see the pattern of input. And when you're lucky, if you're doing this, what you do is you actually surface an implicit object model that was already there. And that does happen. You know that happens when you have a whole bunch, like this is obviously a trivial example. But if you have a much more complex example with many, many more columns, and a pattern emerges when you fill out this kind of a spreadsheet, and the pattern is consistent, that's how you know that there's an implicit object model. And what I mean by an implicit object model, this is some Ruby, but I think it'll be pretty clear what's going on, right? This says link to new controller home action new bill. This is URL for controller home action new bill, right? This here is the implicit object model, right? What you're actually passing in both cases is the same object. It's a thing which has a controller called home and an action called new bill. So one way to, change that is you say link to new, bill home new, and this is a somewhat, how many people here know Ruby? Okay, it's a somewhat contrived example, but it gets the basic idea across. So what you do when you have one of these spreadsheets that has allowed you to determine a pattern in this in some bad code is you create something like this where you know for a fact it's going to be this object with these attributes, and you just have something that produces one of those objects. This is code from Rails. Rails actually has methods that are factory methods that pretend not to be, that produce URLs in this way. Long story short, that's how you know that something's there. And then another thing that you find, like I was doing something like this where I was using a spreadsheet to track the minor differences in highly similar code. And I would find little things like this. This is a pair of console log statements. And they say, I'm afraid of this code, so I made a note to be sure I got this far. And you might think I'm exaggerating, but you see stuff like this in legacy code from time to time. And if you're going through in enough detail to make a spreadsheet of the differences between chunks of highly similar code, things like this, which break the pattern, they stand out. And it's really easy to say, OK, just delete those 2 lines. And this is something that I actually did. This is when I did my first automated refactoring in JavaScript. I created a spreadsheet like this. That was step 1. And then I went in by hand, and I found out all those little like minor variations from the pattern, and I eliminated them by hand. And then I wrote code which went in and identified these implicit objects with regular expressions, and it literally just scanned line by line because the code was similar enough that you could do that. There was an awful lot of copy-paste in it. And when you're doing, when you're refactoring legacy code or something like that, you will see an awful lot of copy-paste. In fact, I really believe, this is a tangent, but I'll get back to the topic in a second. I really believe that you can actually find evidence of fractals in legacy code, right? Because when you copy and paste a bunch of code, that's self-similarity, which is one of the attributes that fractals exhibit. I'm not totally sure, but I did interrogate some math people about it. I was like, math people, tell me. And they said, maybe. Anyway, wasn't that an awesome story? Moving on. So I went through and I found all these things with regular expressions, and I turned this into this with a regular expression. Now this, it kind of seems silly, but it seems silly because there's only 2 of these attributes in the implicit object, right? In the real life example, there was something like 20 attributes. It was ridiculous. This little thing of just hand tweaking it so that it could then be processed by regular expressions removed 1,000 lines of code. 1,000 lines with regular expressions and no changes in functionality. So that was pretty fun. Going back to the spreadsheet, what it actually was an e-commerce site with code for modal overlays, right? So you've got like a modal window. And you see what I did here, right? You got the foo and the bar and all that stuff. What it actually came down to was stuff like the width, the color, and some behavioral controls. So I started with spaghetti and ended up with stuff like this. So you might be wondering, right, that's cool. I don't actually see any robots in the audience, but if, you take this guy as a representative member of the audience, you might be wondering this: where's the code, right? So here it comes. My first code robot project was called Towley, right? Because he's a towel. Right? And there's something that people like to say about good code, which is that it is dry. Right? It stands for don't repeat yourself. And how do you get dry? With a towel. Right? But why use a towel when you can have a towel that has its own opinions? I like to think it makes perfect sense. But I admit that might be hard to believe. So I wrote this in 2008. I wrote it in Ruby, and it targets Ruby. Doesn't do any automated refactoring. What it does is automated similarity detection, which is to say that it can look at a method and look at another method and tell you roughly how similar they are. Or, yeah, actually, if you do that, it explodes, basically, very rapidly. And by explodes, I don't actually mean the code breaks. I mean your computer breaks. It was very, very slow. But it can find similar methods, and it can do, if you want it to find identical methods, it works. If you want it to find methods which only vary by a slight amount, it works. If you want to do anything more complicated, it explodes. So a little while later, I came up with something in JavaScript where I was looking at a blog, and this blog had one of those things where it's like tracking the pinbacks, okay? And the pingbacks included, it was this Discuss thing, right? Everybody knows this this startup, right? Discuss, where they, it's a comment system. And it's got this built-in thing for tracking pingbacks from Twitter, right? So a lot of people had all discovered this thing at once on the front page of Hacker News. So the list of comments was like 100 comments, and 97 out of those 100 comments were, here's the link to this thing, I saw it. And it, is a tweet, right? I mean, they counted these pingbacks as comments, and consequently, it was impossible to see the actual comments. So I just wrote this thing that like opens up the comments, treats them as JSON, and then eliminates highly similar comments. And the way it works is it treats, you guys can't see this at all, right? I mean, this is too small, right? It's okay, you can tell me. Okay, don't. It treats tweets as arrays of words, and then it does set intersection math. And it was much, much faster. I'm going to go over here and show how it works, right? So it's really simple. It uses underscores intersect method. It turns these tweets into arrays, and then it gets an intersection, basically divides the length of the intersection by the length of the array times 100. That's just to produce a number that can be gauged as a percentage. But it's basically just saying a tweet is a bag of words, right? So take these two bags of words, treat them as sets, like an event diagram, and if 50% was the threshold, set arbitrarily in the code. And that was a cool hack, and you can Google Giles Bowkett Discuss blog comment similarity, and you'll find it. Another system that I created uses code from JSLint to identify functions, and then uses that same method I just showed you to compare those functions to determine if they're similar. And JSLint this was the only parser that I could find that was written in JavaScript at the time. This was a few years ago. There's now tons of parsers on GitHub. There's parsers in JavaScript, parsers in CoffeeScript. This was, JSLint contains a parser. And I just bastardized JSLint, I copied it and changed it to, once it found these functions with its parser, throw them in a function array and submit them to the same array-based, set intersection model to determine function similarity. And the reason I did this is because when you're doing refactoring, what you will find in legacy code very, very often is that 2 minutes? Oh, crap. Okay, forget about it. I'll just keep going. Basically, you take console log foo, console log bar, and you can see, there's the Venn diagram. So last but not least, Wheatley, right? I called it Wheatley because it's a stupid AI. Wheatley is a stupid AI from a video game called Portal 2. I made it in 2011, written in Ruby, targets JavaScript. Here's some specs. They're awesome. Okay, this spec describes how the Ruby parser decomposes a JavaScript statement down into an abstract syntax tree. Do you know what an abstract syntax tree is? Hands. Yeah. Okay, fuck. This is an abstract syntax tree. It is a tree of the syntax. So you've got console log foo, you break it apart into a tree, right? Then this is what the tree looks like in Ruby. You can do this kind of comparison, but you can also identify that this thing is a function call, this thing is a raw string. Wow, here's what that enables Wheatley to do. It can wrap function definitions in wrapper functions, identify similar JavaScript code blocks, lots of stuff. It's awesome. Okay, I got about 10 seconds. So to demonstrate this, I'd like to share some of the, wait, we can skip this. That doesn't matter. For example, here's this piece of functionality, extracting the variant tokens by which similar code blocks differ. This is pretty cool, okay? I don't even remember how this code works anyway. Basically, say you've got console log foo and console log bar, and you want to extract the different tokens between these two trees, right? First, you turn it into a tree. See that foo? That's the only thing that changes in the two trees. So you have this code that can perceive these statements as trees and notice the differences, right? And that's what this does. And it does all this other stuff. And it's all about comparing trees. And writing this thing really hurt my brain. And the design includes a lot of crappy hacks, but it has a whole lot of features. And this is a good thing to do. And here's a robot. Thank you very much. I thought that would go quicker. Any questions? What's up?
Can you describe a little bit? You said that you would use this at some point to actually do something. Can you just describe how the output, for instance, of that is useful for you to do the refactoring?
Oh yeah. Okay. So remember the first refactoring that saved me like 1,000 lines of JavaScript? So then I decided it was so cool to have automated refactoring happen that I was going to create a startup called overnighrefactor.com where you upload bad JavaScript and you pay a fee and you get good JavaScript. Then I was making really good progress on this, and I told some programmer friends about it, and one of them told me a story. He said, that sounds a lot like what a professor of mine did at Caltech. And I'm like, really? Wow, that's really cool. I'm like, professor status. And he's like, yeah, Giles, but the reason I'm telling you this is because afterwards he went insane, killed his wife, killed his children, killed himself, burnt down his house, and somehow managed to crash his car. So then I decided not to work on it anymore. But it's really useful for analyzing code, right? Like one of the things, if you're faced with legacy code, it's like a forest, right? And this helps you find your way through it. Any other questions? Okay, great. Oh, wait, go ahead.
How hard and how long did you learn AST has sometimes trees and vary them into?
To figure it, well, so before I did this, there was a project called Treetop in the Ruby world, which got me started on that, and I investigated that. It uses abstract syntax trees, I think. And then there was something else, like it was just like something I read about from time to time, and then I just decided, wow, that's really cool. I should get into it because like I knew, like I had done like one little hack in Rubinius, which is a language implementation, and I was like, wow, language implementation, that's really cool. So I read about it. I couldn't tell you, like I would say maybe like for 2 years on and off, like every so often I would see something about the topic and read about it. And then it would just, like top of Hacker News type of thing, really. Other questions? Nothing? Really? Nothing? Nothing at all? Come on. Okay, I'm done. Thanks.